Okay, Earth Science time. This is Earth Science time. So please take out your Earth Science time. No, but today we are talking about Earth science. Yes, Earth's systems and mapping. The systems of Earth and mapping. Oh, that's going to be so nice. We're gonna have so much fun with Earth systems and mapping. I hope you're taking a piece of paper out. Ouch, that hurts. Oof, you ever have a cough drop and then take a cold drink? But that does not feel good.
You ever had a cold piece of gum and take a cold
drink? A cold piece of gum? I have not.
Like some mint gum.
Mint gum, yeah. I think cough drop might be more severe. So we're talking today about Earth systems and mapping. Let's start with what is a system. You'll notice that if you see up there the CCCs, the cross-cutting concepts, the bottom poster over there, one of them is, the middle one, is systems and system models. Define for me, what is a system? Someone with their hand raised. What is a system? No, I don't want an example. I want someone to define what a system is in general for me. With their hand up, someone is going to do this. Yes, young lady.
Organized group of related objects and components.
That's very good. An organized, someone just made up off the top of her red head. Organized group of related components. I abbreviated even what you said, but that's an organized group of related components. Yeah, I like that a lot. I'm a little suspicious of where that came from, but that's really good. That's really, really good. Would someone, an English professor, that's what they say in the movies when someone says something smart, would someone please translate this to English? What does this mean in your daily speech, Guns?
So I think organized is well enough English.
Okay.
An organized group of
if we're talking about, well, how would a first grader say components? Use it. Things. Okay. Things that do what? They're related. They're organized. They're a group.
Are the same.
Things that are a family.
Things that I'm going to put in quotes work together. I put it in quotes because we use that advisedly. Like, you should understand that most of these things, at least in the way we understand the natural world with our current understanding, they do not have, a lot of these things we talk about do not have agency. They're not making decisions. They're not working together like, oh man, I'm Pluto and I got to go to work today to get around the sun. That's just, they interact.
It's like cogs.
It's like cogs in a wheel. We could say they're working together, but they're not working, like they're not going out to go to their job. Things that work together. So that's what a system is. Things that work together. Now I want 2 examples. Ideally from Earth science. Give me 2 examples of systems in Earth science.
An Earth science?
The water cycle is a system.
I was going to say.
Water cycle. Different components, different things. What are they? Give me some things in the water cycle.
Fish.
Okay, water. Fish. Good. Not wrong, maybe. But okay, so let's think about like rain, a lake, clouds. Those are some things. Are they interacting? Are they working together? Sure. The rain precipitates from the clouds. The clouds condense from the water vapor in the air. The water vapor in the air evaporates from the standing water in the lake. So that's the water cycle is an example of a system. Give you another example.
An ecosystem.
Ecosystem. Okay. Yeah, you're kind of cheating because it has the word system right in it. But an ecosystem, the gopher eats some grass and a hawk eats the gopher. And a fox eats the hawk. I'd have to be a very lucky fox, maybe. But those things are interacting. They are not only fox eating gopher, but gopher being eaten by fox. Yeah, that's an interaction. Really. Photosynthesis. The molecules within the chloroplast of the plant interacting in a way that energy is released into that plant's organelles. Yeah, these are all systems within Earth. Now, we talk about large-scale systems in Earth science. We talk about Earth's, what we sometimes call spheres. Earth's spheres. You should remember this from your lesson self-check. Give me some examples of the spheres of Earth.
Hydrosphere.
Okay, there's one. Hydrosphere.
Atmosphere.
Hydrosphere. Hold on. Lithosphere.
Geosphere.
I will. Yeah, I'm gonna actually put that as geosphere. I think that's what you meant too, Hunter. Hydrosphere, atmosphere, the geosphere. Give me another one.
Biosphere.
Biosphere. The stratosphere and the lithosphere are specific layers that we'll talk about later on in the year, but these ones are the ones that we kind of... The hydrosphere includes all of Earth's water. The geosphere includes all of Earth's rock. I mean, that's what geo means. Earth, the solid material that makes up Earth. The atmosphere, which I might have spelled weirdly. The atmosphere, all the gaseous matter, yet. And the biosphere is all the life. Can something be both?
No.
The water cycle. Give me, what spheres does the water cycle interact with? Obviously, hydrosphere. But is it also the geosphere?
Yeah.
Sure, there's some water stored within rock. That's called an aquifer. Does the water cycle involve the atmosphere?
Yeah.
Of course it does. Yeah, evaporation, the water goes up into the air and is held there. And in condensation, that water vapor is condensed into a cloud and suspended there. Does it involve the biosphere?
Yeah.
Yeah, one of the key traits of life is that all life that we know of needs water to survive. So all of them are kind of interrelated. They are working together. They interact between them. Like the interstate is the highway between states. The interact is when they act between them. Have you ever interacted with one of your fellow men?
Yeah.
Yeah. When you interact, it's not just you talking to them. That's why I like this. That's why we like this discussion. So it's not just me talking at you. We are interacting. You are talking back. You're not talking back, but you're talking back.
Hi.
The cough drop in my mouth is interacting. My cough drop mouth system here is an interaction. The cough drop is changing my mouth. It's making it feel a little better, feel a little bit cooler, making my sinuses feel a little bit better, opening them up a little. But it's also, my mouth is reducing the size of the cough drop. There's an interaction. It goes both ways. An interaction. It is. It's working overdrive. What's the ecosystem? What's the obvious sphere of the ecosystem?
Biosphere.
Obviously biosphere. But is it also the atmosphere?
Yeah.
Yes. Not only the hawk suspended in the air, but the air in the lungs of the gopher as it screams its last scream. Ah! When the fox eats it. The air that the fox lets out as it's like chomping down on the insides of the gopher, right? The little prayer it says before its meal. That's all the atmosphere. What about the hydrosphere? Is that involved?
Yeah.
Yes. The blood pouring out of the gopher's wounds. That's primarily water. What about the geosphere? Does that interact with the ecosystem? Where did the gopher live before the fox got him?
In the ground.
In the ground. And the fox had to get down in there to get the gopher out. Photosynthesis, obviously that's biosphere. But you see where I'm going. We could say it's related to all of these things too. They're interacting. Those are the Earth's systems. The Earth's systems. Do you have questions about Earth systems at all? The various systems of Earth? Let's talk a little bit then about some of the ways that we show this. And the way that one of the most important ways that we show Earth systems is in mapping. Does anyone still need the points here? It looks like some people are still writing. Am I okay to erase all this?
Yes.
Does anyone not think I should erase all this? Okay. So Earth's systems, those facets of planet Earth that we study, are often expressed in models, which we often call maps. A model of Earth. Give me an example of a model of Earth. I can see a couple in here. Yeah. Would you actually, Kirsten, would you carefully, please, retrieve that globe from the ceiling? I want to use it. But in the meantime, I got this. Ooh, look what this represents.
Earth.
What class is this?
Earth science.
Earth science, and this is plain Earth. Yep, there you go. You have to kind of lift up on it a little. Ooh.
Hey, can we record this?
We better not. Good, thank you. Just hold on to it for a second, Carson. So check this out. This is your boy Earth. You are here. You are on it somewhere. I mean, obviously you are not here. This is a model. Let's talk about what a model is and isn't, first of all. Is a model a perfect representation of something? No. Well, in fact, we could even define it as an imperfect representation. In what way is this model imperfect? Now, imperfect doesn't necessarily mean bad. Let me remind you that in English, the perfect tense of a verb means that thing has been completed. So that just means this is not all the way there. It's just not. Yeah, the size, an unrealistic size, frankly, for a planet. So it's an imperfect representation. Do you know that if planet Earth were scaled down to this size of a cue ball, that it would be the smoother than any cue ball ever machined? Because because if we were to draw Earth to scale, which that's a pretty good scale model, the highest mountain, Mount Everest, is about, I don't know, 3 miles-ish tall, and the lowest point on Earth, Marianas Trench, is about 4 miles-ish deep, and the difference between those is about, like 7 miles. And the whole width of the Earth is much, much bigger than that. And so, smoother than any cue ball ever machined. So really, this is an imperfect model in that it's too rough. This is too rough to be planet Earth. The roughness is exaggerated. What else is imperfect about this? It's not made of the same stuff. It's not made of the same components. Where's your mom's house? Well, it's not on here. It's not represented. The scale is too large. You can't. It doesn't have everything, right? Here's China. Where's the factory where they made my pants for 2 minutes? It does not have everything. It doesn't have everything that planet Earth has in actuality because it's a model. It's an imperfect. Now, does the fact that it's imperfect mean that it's useless? No. Even this kind of silly little model is useful. Like maybe you didn't know. I bet if your bell work was pass this around and write one thing that you learned about planet Earth's surface from this, you probably would learn something, right? Like maybe because you're used to seeing a map. Oof, this is going to be a mistake. Because you're used to seeing a map and you think Antarctica is thick, and you notice that it's actually almost the same size as Australia on the globe, you might have learned that from this, although you might have already known that. This is not a Mercator projection, but it's very close because we are going to talk about projections. This, it tells us on here somewhere, I think it's a Robinson projection. Where does it tell me about its projection? I kind of wish that I didn't write this up here yet or pull this down yet because I wanted to write a little bit more about it, but, well, here goes. It worked! Hurrah! The shark got his arm pinched, but that's okay. So, one of the things that we need to understand about the Earth in reality is an almost perfect sphere, isn't it? It's actually an oblate spheroid, meaning it's wider in the middle because it spins like Luigi at Luigi's Pizza spinning the pizza dough out. But it's almost a perfectly sphere. Almost a perfect sphere. That makes it hard. Oh, let me ask this as a question instead. Why does that make it hard for us to map planet Earth? What's convenient about the format of most maps being flat? Yeah, okay, you can turn to a page in your book, which if you have your book out and it's covered, I do not want to see an uncovered book. But if you turn to let's just turn to page 31 real quick. You can see, I'll show you on the camera. You can see there is Kimberman. There's a map there, and it's nice because it fits in this flat book because it's on a flat piece of paper. But guess what? If I want to have my slightly better representation of Earth, it's fine. It just bleeds papers. Don't worry about it. This is why mapping is important. Stop. That's why, because that doesn't work good. Okay, that's exactly it, Hunter. That's exactly it. So we have this spherical thing, and we want to be able to make it flat. We have a couple of different choices, and these are called map projections. Map projections. They're ways of representing, fill in the blank, ways of representing what?
A sphere.
Yeah. a sphere on a flat surface. And they always involve trade-offs. Like you're always going to be getting something at a cost. Looking back, let's see how many times I can do this and not screw it up. Looking back at this one, we know, or you probably are aware, that a trade-off is that these sizes are not to scale. Right? We know that these two things are roughly the same size on the real spherical Earth, but on this map, Antarctica is thick and Australia seems really small. That's because the nearer we get to the poles on this projection, the wider things seem to be. You know, the South Pole is a point and the North Pole is a point. But on this map, that single point is expanded to be this whole line. And so all of it seems to get bigger. Yes?
They're liars.
Yeah, in a way it's kind of like lying, but also it's not really, because we're not doing it maliciously. We just can't do it perfect.
There's an app, and it's like the true size up, and it's a Mercator projection.
Yes. A Mercator you said a Mercator projection earlier, and I'll tell you were very close. The Mercator is a kind of cylindrical projection, which we'll talk about in a second. But the only difference is that this one, which I think this is a Robinson projection, instead of being an actual rectangle, it kind of like brings it into be closer to a point on the top and bottom. So there we go. Up she goes again, working even better. So we can use a cylinder. If we put this is supposed to be a sphere. If we want to make it into a rectangle, we can put a cylinder around it, which that's supposed to be a cylinder. Kind of like, I'll just use this piece of paper that fell out of my book. Like this. So we want to make this sphere onto this piece of paper. We can wrap it in a cylinder like the Mercator projection. And look, imagine if that little sphere in there was emitting light, the place where the light was touching. That's why we call it a projection. If we projected light out of that sphere, the place where it touches, we would draw on there, and that's how we make a map projection. So a Mercator projection is a cylinder projection. And a cylinder projection is usually pretty good at retaining shape at the expense of size. The trade-off is, for a cylindrical projection, we get the rough shape, but the sizes are all wrong. Yeah.
What if the Earth is flat?
Cool. Great question. What if the Earth is flat? It isn't. So that would make it a lot easier to map, though, if it were. Another kind we have is a conical projection, where we can make a cone out of our paper. And this is good for kind of both shape and size, but only for a certain area. Like it gets worse and worse the further away from a certain area you get. And so we have a conical projection, is where we use a cone. See? And then the other one is called a gnomonic projection, where it's a single point. We just like rest it, and then it's really good at that single point, and the further away you get, it gets much, much worse. So the kinds of projections we have are cylindrical, conic, and gnomonic, gnomonic. I'm sorry, I'm writing your way, Colin. So these are different ways to get the surface of Earth, a sphere, projected onto a flat object. So this Robinson projection is a pretty much a cylindrical projection. The shapes of these things are roughly the way they are in real life, but the further away we get from the equator, where it's expected to be almost perfect, the further away from the equator we get, where the cylinder is kind of touching the sphere, it gets worse and worse. Now these two, because someone recognized the drawbacks of the Mercator projection, well, it's not a Mercator, the cylindrical projection, they also put these gnomonic projections centered at the poles up here, so that if you're dealing with stuff that has to do with the polar regions, it's really good near the poles, but it gets worse and worse the further away you get. That's a gnomonic projection. So these two are gnomonic projections. This one is a cylindrical projection. There are some other things about this map you can see I've drawn on here. What's this? You should write this down. I'm not going to write it down because I'm not going to write on the map anymore, but a compass. You should write that down. A map usually has a compass. A map usually has a compass, or sometimes we call it a compass rose.
Why would we call it that?
Because it looks like a rose.
Yeah, because it looks like a rose, because it rose out of the grave. Because of the rose of the movie theater. because of Rose from the Titanic.
Jack.
And then he's on the door and he goes northeast, southwest.
Don't do that. You're gonna make me cry. Another thing this has that I have written here is a scale, a map scale. You should write that down. A map scale, SCALE. A map scale tells us how big things are on the map compared to real life. This one, the scale on here is 1 to 24 million. You can see I tried to write that at one point. 1 to 24 million. What kind of numerical expression is this where we have one number as it relates to another?
Ratio.
A ratio. The ratio, a map scale is expressed as a ratio. Write that down. A map scale is expressed as a ratio, and this one is 1 to 24 million. Meaning, you'll notice that the ratio has no units. It's unitless. The ratio is unitless, which means that it doesn't matter what kind of unit we're using. A foot on this, or let's use a meter. A meter on this, bam, is 24 million meters in real life. So the distance between the Cape of Florida and the center of Australia on this map is a meter, yeah? So in real life, the distance between those two things is 24 million meters. Okay, what about pencil? What about Dalton's .7 lead pencil? Well, the distance between the delta of the Nile and let's find another kind of remarkable point. The center of France on this map is the length of this pencil. In real life, it's 24 million of these pencils. That's what this scale means. You don't have to use any particular unit. If you're using inches, maybe it's an inch between Crawford and Cheyenne, Wyoming on here. That's 24 million inches in real life. Does that make sense? That's how a map scale works. You should write something about that down.
Not every map is built like that.
They're not all 1 to 24 million, right? You get but every map has a scale. Because one of the drawbacks, one of the reasons we have to model Earth is because we can't use a scale model. We can't have everything be the same size, otherwise we just have a second planet. So we want the map to be a representation of a sphere, which is difficult, and we want it to be smaller, which is difficult. The center of France somewhere.
Pencils are 24 million feet long.
Yep. How do we, I'm going to pull this down. Let's see how many times I can do this in a video without messing it up. How do we indicate coordinates? You know what the word coordinate means? You should know that from math. How do we indicate coordinates on the map? Yeah. Thanks. He raised his hand. But okay, those are specific ones of latitude. Latitude are the east and west coordinates. You should write this down. Latitude are east and west coordinates that go north and south of the equator. So the lines run east to west, but they measure north and south of the equator. Longitude run north and south, but they measure east and west of the, you know? Mm-mm. Nope. This one, 0 degrees of latitude is the equator. Look at this line I'm drawing. Everyone stop writing right now. Look at this line I'm drawing. Do you see it? This is the... I missed. This is the... Oopsie daisy. That's the equator. I need to erase that first one because I missed. This is my job. This is my degree. Okay, I'm going to erase this top one. Okay, so that blue line I drew is the equator, which is a line of they're flat, so it's a latitude. That's how you remember it. Latitude, flat, longitude, long. I don't know how that helps you, but it helps me. The equator is a line of latitude, and we measure distances north and south of the equator as degrees of latitude. So you can see 42 degrees north of the equator I have here. Where do you think I'm putting this dot, or trying to put this dot? Crawford. 42 degrees north of the equator, and 103 degrees west of we use this line. 0 degrees of longitude is does anyone know? Prime meridian. You should write that down. 0 degrees of longitude is the prime meridian, which is an arbitrary line that runs through Greenwich, England, which is where the there was some observatory there where they first decided to do this. Like it had to be somewhere. In the metric system of Napoleon's time, they had it run through Paris, but it runs through Greenwich and not super far off of Paris. So the 0 degrees longitude is the prime meridian. 0 degrees latitude is the equator. And we measure north and south in latitude and east and west in longitude. And then we can use that coordinate grid to find anywhere in the world. Crawford's coordinates I have here, 42.7 degrees north, 103.4 degrees west. That's latitude and longitude.
Is it true that the pyramids of Giza are like on a specific?
Yeah, someone's been watching too much History Channel, but yeah, someone said the pyramids of Giza, which are down here-ish, are on some certain line of latitude. Sure, I mean everything's on a certain line of latitude, but I know there's something spooky about it. Or if you get, I don't know, Chichen Itza, yeah. Another thing that kind of relates to latitude and longitude is, we're going to run out of time here pretty quick, but is the time zones, which time zones work basically so that the same amount of sunlight is experienced at a given time. There are 24 time zones to represent the 24 hours of the day. We got a couple things left that I need to talk to you about before we can go. One is we have this idea of map view versus cross-section. And we use this all year long, so I'm just going to bring it up now. If we're looking at something like a bird's eye view, that's called map view from the top. Like we're looking at it from the sky, that's called map view, like we're looking at a map. Cross-section is from the side. It's as if we were looking at, so like if I look down at my cup from the top, that's like map view. And if I look at it from the side, that's like cross-sectional view. And a lot of times we'll label those. A lot of times we'll label things so that we know whether we're looking at something from the side or from the top. And then the last thing is the idea of a topographic map, which I'm afraid you'll have to do your own research in because we've run out of time. But we'll talk more about it tomorrow when we do we've done a little bit of a lab about it. So these represent topographic maps where you can see in real life it's three-dimensional, right? But on a map, we don't want to, once again, that don't work really good. Do you see? That don't work really good. And so what we do is we look just to the top and we represent these lines of elevation as concentric lines on a topographic map. We'll do more of that tomorrow in the review. This was really fast. You have questions about maps? I hope I'm getting a phone call.